Hello everyone, this is the second part of a chapter 1, that is semiconductor diodes, and in this video we are going to learn about the Zener diode. Zener diode is a special type of PN junction semiconductor diode. Its construction is similar to that of a conventional PN junction diode. However, in constructing the Zener diodes, the reverse breakdown voltage is adjusted precisely between 3 volt to 200 volt. Its applications are based on this principle, hence Zener diode is called as a breakdown diode. The doping level of the impurity added to manufacture the Zener diodes is controlled in order to adjust the precise value of reverse breakdown voltage. So here the circuit symbol of Zener diode and the real component appearance is given. So here this black strip, this marks the cathode. Zener diodes are normally used only in the reverse bias direction. It means that the anode must be connected to the negative side of the voltage source and the cathode must be connected to the positive side. After increasing the reverse biased voltage, at the beginning a reverse leakage current occurs, and this current slowly increases with increased VR voltage, that is reverse voltage. At a particular voltage, a very sharp reverse current increases sharply, and this voltage is known as a Zener breakdown voltage. Because of this property, Zener diode is used as a voltage regulator. It is primarily used to regulate the circuit voltage as it has constant Vz. A large change in IR, that is reverse current, will cause only a small change in Vz. It means that a Zener diode can be used as an alternate current path. The constant Vz developed across the diode can then be applied to a load. Thus, the load voltage remains at a constant by altering the current flowing through the Zener diode. Biasing of the Zener diode. So we can bias this Zener diode in a forward mode. So this is the forward biasing of the Zener diode. So when the anode of the Zener diode is connected to the positive terminal of the DC source and cathode is connected to the negative terminal, the Zener diode is said to be forward biased. And the forward characteristics of a Zener diode is shown in figure. So it has almost identical to the forward characteristics of a PN junction diode. So here we can observe that the forward characteristics of Zener diode, they are similar or equivalent or ideal with the PN junction diode. Reverse biasing of a Zener diode. So here this schematic diagram shows the reverse biasing of the Zener diode. When the anode of the Zener diode is connected to the negative terminal of the DC source and cathode is connected to the positive terminal, the Zener diode is said to be reverse biased. The operation of reverse biased condition is substantially different from that of a PN junction diode. So here the reverse characteristics of the Zener diode are shown. So here when the reverse voltage is less than the breakdown voltage, then very small current flow through this diode, that is called as a reverse saturation current. When the reverse voltage is equal to the breakdown voltage, suddenly the large current, sharp current flows through the diode. So here the region between this Iz mean and Iz max is called as a Zener breakdown region. So this is the IV characteristics of the Zener diode. So this is forward bias region where it is identical with the PN junction diode, and this is the reverse bias region or a Zener breakdown region. So here the after breakdown voltage, sharp increase in the Zener current that is appear in this region. So it is almost for forward bias characteristics, they are almost identical to the forward characteristics of a PN junction diode. And the reverse characteristics, when the anode of the Zener diode is connected to the negative terminal of the DC source and cathode is connected to positive terminal, the Zener diode is said to be reverse biased. As we increase the reverse voltage, initially a small reverse saturation current IO, that is also called as the IS, that is reverse saturation current, which is in a microampere, will flow, and this current flows due to the thermally generated minority carriers. At a certain value of a reverse voltage, the reverse current will increase suddenly and sharply, and this is an an indication that the breakdown has occurred. This breakdown voltage is called as a Zener breakdown voltage or a Zener voltage, and it is denoted by Vz. The value of Vz can be precisely controlled by controlling the doping levels of P and N regions at the time of manufacturing a Zener diode. After breakdown has occurred, the voltage across Zener diode remains constant equal to Vz. Any further increase in the source voltage will result in the increase in a reverse Zener current. The Zener current after the reverse breakdown must be controlled by connecting a series resistor R in a series with the Zener diode, and this is essential to avoid any damage to the device due to excessive heating. So here is the Zener region and it's important. So this is the Zener region between the Iz main and Iz max, and this is occurred after the breakdown. After reverse breakdown, the Zener diode operates in a region called Zener region as shown in figure, and in this region the voltage across Zener diode remains constant but current changes depending on the supply voltage. Zener diode is operated in this region when it is being used as a voltage regulator. The complete VI characteristics of Zener diode is shown in figure. So here the applications of Zener diode. It is used as a regulated power supply in the protection circuits for MOSFET and op-amps, in the clipping circuits, in the pulse amplifier, and this is the main application of a Zener diode, that is the Zener diode as a voltage regulator. So here first regulating action with a varying input voltage, that is constant IL. So here actually we are varying the input voltage, and here load, that is this is constant, and that's why as this resistance is constant, the current flowing through this resistor, that is IL, is constant. So as IL is constant, the load resistance RL is constant and Vin is varying. So as IL constant, RL is also constant because IL equals to Vz by RL. Here is the this Ohm's law is given, that is I equal to V by R. So as load resistance is constant, load current is constant, that means IL is equal to Vz by RL. So here RL and IL both are constant, but supply current keeps changing due to change in Vin, as I equal to, that means the total current or the current because of this input voltage Vin is given as Vin minus Vz. Vz is nothing but the voltage drop across this Zener diode divided by the series resistance Rs. Also I is equal to Iz minus IL. If we increase the Vin, what happens? Then I will increase because I is depends on the input voltage Vin. Then after increase in I, but IL is constant, as IL is equal to Vz by RL, that is IL is depends on the voltage drop across this diode Vz and the load resistance RL. As the value of this RL is constant, IL is constant. Hence Iz increases. As the I changes, input current changes and IL is constant, that's why Iz will increase. Iz is nothing but the current flowing through this Zener diode, as Iz is equal to I minus IL. So if this Iz is less than Iz max, Iz is increasing, but if it is less than the Iz max, then the Zener operates in the Zener region and output voltage remains constant. If this Iz is less than Iz max, then the output voltage remains constant. Now, if Vin is decreases, then I will decrease, but IL is still constant because IL is equal to Vz by RL. Hence Iz decreases because Iz is equal to I minus IL. If this Iz is decreasing and it is greater than Iz mean, then the Zener operates in the Zener region and output voltage remains constant. So in this way, if the input voltage changes, then also the output voltage remains constant. That means it regulates the output voltage. Now the second, if we are keeping the input voltage constant but varying the load, that is V in is constant and here the load is variable. So here we assume that input voltage is constant and load resistance RL is variable. So if RL is increased, then IL will decrease. But the total current I is constant as it depends on the V in. So it is given as V in minus Vz divided by Rs. And I is also given as Iz minus IL. So if RL increases, IL decreases. If we increase the resistance of this load, then the current flowing through this resistor will decrease. But I is constant because Iz is given as, and the Iz is given as I minus IL. So Iz will changes. That is Iz will increase. But as the Iz increases, VO still remains constant as long as if Iz is less than Iz max. And if we decrease the load, then the load current IL will increase, but I remains constant and hence Iz decreases. But output voltage remains constant as long as Iz is greater than Iz min. So in this way again, the using Zener diode we can regulate the output voltage even though the load is variable. So here are the questions based on this topic. Solve the questions. Thank you.